Hello everyone, I am Runze fan from Beihang University, Beijing, China. Our paper is Fov-GS, Foveated 3D Gaussian Splatting for Dynamic Scenes. This work is together with Lili Wang, Jian Lizhi Zhao, and Qixiang from Beihang University, Xuehuai from Nanjing University of Posts and Telecommunications. 3D Gaussian splatting represents scenes as a set of Gaussian ellipsoids and achieves photorealistic rendering with speeds of over 100 frames per second for static scenes. However, the rendering performance of Gaussian splatting in dynamic scenes drops below 10 frames per second. The motivation of our method is to improve rendering performance for VR applications. One possible solution is to reduce the number of Gaussians needed for deformation and rendering. However, simply ignoring the Gaussians can cause missing parts. Foveated rendering is an accelerated rendering technology that allocates computing resources based on human visual system perceptual models, providing an idea for reducing the number of Gaussians. Bernhard in 2023 proposed the 3D Gaussian splatting method, which has become a prominent technique in computer graphics. Yang in 2024 extended static 3D-GS to dynamic scenes by constructing a deformation field for all Gaussians. Wang in 2024 combined Gaussians with control points, which achieves the control of the motion of the dynamic Gaussians. Foveated rendering provides an acceleration technology for VR applications. Genter 2012 used foveated graphics to generate a 3-layer image with different resolutions using one rasterization pipeline and composited them to generate rendering results. Weyer in 2016 integrated ray tracing to the foveated rendering, but it is limited by performance. Meng in 2018 proposed the log-polar foveated rendering method to accelerate foveated calculation in the log-polar space. To achieve photorealistic and real-time rendering for dynamic scenes with Gaussian splatting in VR applications, two challenges must be addressed. The first one is, foveated rendering cannot be adapted to the 3D-GS pipeline directly due to foveated rendering is processed in 2D screen space, whereas Gaussians are distributed in 3D space. The second one is how to perform Gaussian splatting aligned with the perception of the human visual system. We propose a foveated 3D Gaussian splatting pipeline to address the above challenges. There are 3 steps. Step 1 is dynamic static separation-based 3D Gaussian forest initialization. Step 2 is deformation field and Gaussian decomposition-based 3D Gaussian forest optimization. Step 3 is HVS models-based 3D Gaussian forest rendering. Similar with 3D Gaussian splatting in Step 1, we first train initial Gaussians in canonical space. Then we add an additional property to each Gaussian, a dynamic property, where dynamic indicates that the Gaussian represents a dynamic object, and static indicates that it represents a static object in the scene. We separate the dynamic and static Gaussians by iterating through all the training views in chronological order to update the dynamic property. Next, we initialize the Gaussian forests based on the 3D size and semantic property of the separated Gaussians and construct sets of static and dynamic Gaussian trees. In Step 2, we first optimize the dynamic Gaussian trees. Fov-GS optimized Gaussian in canonical space and the deformable field jointly with a stop gradient operation, which leads to suboptimal optimization of them. We propose a deformation field and Gaussian decomposition-based optimization method to address these problems. To be specific, we first perform a masking operation on ground truth image based on dynamic mask due to deformation field and dynamic trees should only model the dynamic objects. Then, we assume that the Gaussians at time pre have been perfectly optimized. Therefore, the image loss at the current time is solely due to the inaccuracy of the deformation field, and we optimize the deformation field based on this loss. Next, we use the optimized deformation field to calculate the deformed Gaussians at the current time. At this point, the image loss is entirely due to the inaccuracy of the dynamic Gaussians, and we optimize the Gaussian properties based on this loss. For the static Gaussian trees, we perform a masking operation on ground truth image based on static mask and optimize the properties of static Gaussians. In step 3, we render the 3D Gaussian forest to foveated images based on the human visual perceptual models. The core of our rendering method is selecting appropriate layers of Gaussian for each tree according to the acuity model and the contract sensitivity function model during rendering. For trees in dynamic forest, we first select Gaussian layer to be deformed based on the acuity model, and deform them, and then select Gaussian layer to render based on the CSF model. For trees in static forest, we directly select Gaussian layer to render based on the CSF model. The foveated image is rendered by simultaneous rendering the selected dynamic and static Gaussians. We first compare the performance of our method and DGS. DGS extends static 3D Gaussian splatting to dynamic scenes, but the rendering performance is inefficient, with frame rates dropping below 10 frames per second in complex scenes with millions of Gaussians. Compared with it, our method achieves real-time rendering with the rendering speed improved by 7 times, reaching 60 frames per second. We visualize the rendering results of our method and the DGS method. The lower left of the left image shows our result. The upper right shows the ground truth. The right are the close-ups of the results. DGS renders full resolution images, while our method renders foveated images. Compared with the DGS method, our results are closer to the ground truth and preserve sharper details in both foveal and salient regions, especially for the dynamic objects. We also compare our method with ground truth, DGS, and MSGS. Compared to DGS, although our method uses fewer Gaussians for rendering, our results demonstrate higher similarity to the ground truth, such as the blue flame of the blowtorch in the foveal region. Compared to MSGS, our results are closer to the ground truth in both foveal and periphery regions, such as the text on the blowtorch and the flame on the chocolate. In the Americano scene, our method also achieves higher rendering quality in the foveal and salient regions compared to the DGS and MSGS. Our method renders the flow of coffee into the cup, the diffusion of the coffee into the water, and the handheld cup, with more detail. This table shows the comparison of PSNR and LPEPs of our method and previous methods. Our method achieves higher PSNR and higher LPIPs in the fovea and salient regions than those of previous methods. In conclusion, we propose a 3D Gaussian splatting method for foveated rendering of dynamic scenes. We introduce a 3D Gaussian forest representation for dynamic scenes. We propose a dynamic static separation-based forest initialization method to construct the 3D Gaussian forest. We introduce a deformation field and Gaussian decomposition-based forest optimization method to optimize the 3D Gaussian forest and deformation field. We propose a HVS models-based 3D Gaussian forest rendering method for efficient foveated rendering. Our method has several limitations. The first limitation is that the quality of the dynamic static separation is strongly influenced by the quality of the input semantic segmentation. The second limitation is that the rendering performance decreases for scenes containing objects with fast motion. In future, we intend to refine the separation by calculating motion consistency. And we intend to predict deformation along with the speed and direction of the objects. That's all. Thank you.